So we have 4 out of 9 students, so it's not bad. But just less than 50% attendance. So, okay, we're going to start chapter 3. Chapter 3 is correlations and a spectral density function. So now we are approaching to core of the course. So this correlation, when you say correlation, of course that's time domain function. Correlation, time domain function. And the spectral function or spectral density function, that's of course what domain? Frequency domain function. And in chapter 2, as we cover the probability function, then in chapter 1 and 2, we look at the time domain function versus Fourier transform. So Fourier domain function, that's what we discuss, all the basics. Now, next higher level is a correlation function, time domain function, versus frequency domain function called the spectral function. So you need this spectral function. Why? What does it do? Spectral domain function. The frequency domain function, it shows the frequency content in the given, the measurement, things like that. Then frequency content is like investigating the personality. I mentioned about the personality, what frequency components is there. What would be the toner frequency, driving frequency and all that. Then you can throw back and forth. Then to do that in the frequency domain function, something like, as I mentioned, spectral function, you need both the magnitude and the phasing informations and all that. And when you said the correlation, it's like y is equal to, for example, ax plus b. X is, the y is dependent to the x, plus some noise could be in there. Noise could be usually lots of the problem falls in the independent noise, but not necessarily independent, sometimes dependent. When two random variables are dependent each other, degree of the complexity of the problem is much higher. So rather than solving nonlinear equation itself as is, but lots of situation, as you might notice through any journal paper, they use piecewise linear to make life easier. So think about that too. You may not have to solve nonlinear, which is very difficult sometimes. Then piecewise linear, much easier. Of course, with the arrow involved in there, but you could, with a small arrow, you could survive that. And let's look at first the correlation function. Correlation function is concerned is like a classical correlation function. So it's a degree of correlation is what you first look at it. Then when you say correlation between x and y has a correlation. then immediately you have to think about the correlation coefficient. I briefly mentioned about the correlation coefficient. So you have to deal with the correlation coefficient. Then depend on the algorithmic process or stationary process. The algorithmic process would be much easier. Why? Because one time history they represent the whole ensemble of the process. So this is about the 4 different class of the correlations, classical correlation between like X and Y. So classical, simplest one is showing here. I mentioned before, like cantilever beam, and did I use X as a loading? X, and deformation is like Y, but we use usually the force which is a P, right, loading, and the deformation I use as a delta, the vice versa. So you can generate the table. So for the linear elastic, the approach, the relation between X and Y is pretty linear. But after it passes the yield, then there will be a permanent deformation. Then the permanent set start to form up. Then that's a nonlinear. So perfect linear correlation is like this. This is a measurement point. So this case, the relation, classical correlation between X and Y is perfect linear. So this case, first one is Y is equal to AX plus B. So perfect, this is a perfect linear. The reason I'm writing, even if it's there, what I feel is I can just go through in 10 minutes, everything is all, then I can finish, okay? But I always discover myself, if you just look at it, then close the note, then try to derive the relation, 9 out of 10 you will fail. 9 out of 10 I would fail, I guarantee. So that you have to be, as I mentioned before, be careful using the PowerPoint. You think you know everything. Close it, derive the relation, fail. By the way, I was going to announce it. Next week, I'll be out to conference. So whole next week, Monday through Friday. I'm leaving Monday morning and coming back on Sunday. I'm going to leave from the state, U.S. on Saturday, but I'll get here Sunday, I think 5 o'clock. So next week, no class, but week after, anybody has a calendar? Week after is the 21st, I think. March 21st is a Monday. I'll give 1 hour the makeup class at 6 to 7. I talked to Mr. Num, so he knows about that. And every Monday is like 6/27 is Monday? 28 is a Monday. So I'll cover one more hour at 6 to 7. And the next is April 4th is Monday. 6 to 8 p.m. I'm going to give you the exam. So I have to give you the exam. I don't want to give exam, but I have to give you exam. So whatever I covered up to the content the Friday before, so which means 4, 3, 2, 1, up to the April 1st content, then I have to give you some exam. It's going to be comprehensive exam. I can knock you out, but that's not the intention. Intention is to just to check out all the basic stuff, whether you properly understood or not, some definitions and all that. And whether it's going to be open book or closed book, I'll think about it, okay? Depend on the problems that I will prepare, then I'll let you know. At least a week before, but you should master pretty thoroughly. So far, mostly all the definition types is what I cover. That's what you need for these topics, okay? So next week, no class, so you can really prepare. You could prepare quick. It's not that. I'll ask Higyu to send the email to do this. Then after this, it's gonna be all okay. And the week of 21st, the Friday is what? Friday is 25th, right? March 25th is a Friday. Yes. Friday, no class. I'm going to take a day off. We professors, our group, supposed to take a hike to the mountain, but then I was going to take a day. That's the reason. But they switched to March 24th because Professor Paul Berrigan is coming. So we're going to all go together. But anyway, no class on 25th. Then I will make out like a full classes, okay? So I think everything is all fair. That's what. All clear? Youngbin? Clear? So perfectly linear relationship. That's the basic classical situation. But when you conduct the experiment, it's not going to be perfectly linear relationship at all. A lot of times there is a dispersion. So dispersion is what the graph B is talking about it. It is scattered, but it's not that bad, but still scattered. Then you can really, using the regression analysis or minimum criteria, you can really generate the linear relationship using the regression analysis, as I will show you what that is. Then you can approximate the overall measurement as a linear relation, but which has spread. So this is called something like a moderate linear relations. So third is kind of a perfectly linear, the nonlinear. Third is functional. It has a functional relationship. You can write the equation, not the linear equation, nonlinear equation. So this is really nonlinear relation. Nonlinear, which is really functional relation. We can write that. And lastly, what's the last to be? It's just a scattering is totally unpredictable. Okay? It's purely the random. So last relation is purely the random situation. Random relations. You can draw the as approximation some nonlinear curve to fit the spread of the measurement. But as I mentioned before, it's cold here a little bit. Don't you feel cold? As I mentioned before, when you get the signature, basic measured usually time history, you have two components. One is a static component, another one is a dynamic component. But static component, you can add, you can delete, you can handle that afterward, right? So, for example, the anything, this relation, another one is could be like this. Doesn't have to be like this. Could it be like this? But the spread could be here. Then you can approximate like this. You can get the CG, center of gravity, or center of the spread, right? So in this spread, you can say, well, my CG is right there. Then you can, of course, shift x, y. So in other words, mean value you can spread. So you can reset the x-y axis right from here to here. Then the mean value, you don't have to worry. You can delete for analysis. You can bring back afterward. So that's the another good situations. Pay attention on this. I'm going to show you the regression kind of analysis here. As shown in figure 3.1b, B is a moderate linear relationship. We wish to express and approximate the functional relationship between x and y in the form of a straight line. We want to approximate as a form of the straight line here, okay? Minimize the square of the deviation of the actual values of y from their values predicted by the straight line approximation. Then of course you can adjust the position so that what's the EX? Expected value of X, expected value of Y, or that's a mean value of X and mean value of Y. You can set equal to 0. Then you can shift into the mean, or CG is the same thing. And then you can get the deviation. The deviation, then you can make a square of the deviation. Then you can minimize the deviation in such a way that M fits the best. M means over there is a slope, right? That's what we are using it all the time. So usually I'm going to reset 0. This 0 is really CG, where the mean happened to be the value. We shifted XY right into that point. Then you can draw the straight line approximation. Then let's say we didn't know M yet. Y is equal to mx. And when I pick it up any value of the x here, and this is a measured point. This is x, right? This is a measured point. Measured point, you have a particular value of the, let's say, y. But from here to here is the value which is mx. So deviation is here. This is a deviation. So this deviation, delta, is simply what? Y, measured point, minus mx predicted. Okay? Then idea is to minimize the square of the deviation. So delta square is equal to, of course, y minus mx square. We're gonna minimize it for which is called the regression line of y on x. That's what you call this line when you put the x and y here. But sometimes with reasoning, why it could be x, then I can just draw the line here, said this is experimentally measured point, and this is my, and this guy could be a delta. So you can have deviation is equal to, so x, this point is x minus my. So you can just do the same approach to get the minimum, to determine the m, okay? To determine the m. So that's what over there. Okay, so I'm going to take the expected value of del square. That's what I'm doing right up here. Then idea is take a derivative of expected value of the delta square, discrepancy square, then take a derivative with respect to m z equal to 0 to minimize, totally minimize the deviations. Okay, that's what it does. Z equal to 0. Then to determine what? To determine the actual m value. M is simply slope, okay? So if you do that, so expected value, let's do few. So y minus mx square, which is equal to expected value of y square minus 2mxy plus m square x square. Then you can apply to each. So if you apply to each term, then you have e to the y square minus 2m. M is a constant, right? So 2m e to the xy plus m square e to the x square. Is it all correct? Yeah. Then this is equal to, what do you call that? Now over here, we shifted the center to the O, point O, the origin. So I can say Ex is equal to Ey is equal to 0. Can I do that? Of course, right? We shifted, right? Static portion, just to put it out. So this, because the mean value of x and y are equal to 0, I can say that sigma y square. Can I do that? On the condition expected value of y is equal to 0, right? So sigma y square is equal to e y minus, mean y square. I decided that we'll write a little bit more because later part is really confusing. So I'll slowly step out, then you can fairly catch up. Then there will be no confusions, okay? So this is minus 2m e to the xy plus m square sigma x square. Then what do you do? Then I'm going to take the derivative e del square, take a derivative with respect to m, then set equal to 0, then to determine the value of the m, which is most optimum for the moderately distributed the measured the data. So I'm going to take a derivative. So if you take the derivative, which is equal to, of course, 0, here is what? Minus 2 exy plus 2m sigma x squared has to be equal to 0, correct? Yeah. Yeah. So then m is equal to 2 cancels up. So m is equal to sigma x squared. This is simply e to the x y. Because we know here e to the x and e to the y is equal to 0, happen to be 0. If you set the origin from here, not here, way back down here, you have to take into account the mean value in there. So here, this guy, anybody remember this guy? What you call e to the x minus mu x y minus mu y. What did you call this? So here, the mu x mu y in this problem set happen to be 0. That's why this is equal to e to the x y, right? Because this is equal, because e to the x, e to the y is all equal to 0. You remember the covariance? It flew away, right? That's what happened. It's new terminology. It just goes away if you don't think about it. So this is called covariance. Okay. If x and y are totally independent assumption, in this problem, you can't assume because y is totally related to x. It has a degree of the relation, correlation. But if I say, if this is really uncorrelated, sometimes use the word uncorrelated, which is really same as independent. That's what I'm using, that's what the people use. If it's uncorrelated, then what happened? This guy is equal to 0. Uncorrelated, this guy, I'm going to write here, EXY can be rewrite as e to the x, e to the y. This is mean is equal to 0 in this case, but also no correlation, then you can tell right away this guy is always 0. If noise and x uncorrelated is equal to 0, if it's uncorrelated, if it is independent. Noise source is, if noise source is independent, noise is coming from the motor sitting on the floor, okay? So when you take a measurement, the velocity of the motor, then noise source is not part of the motor, is something else, okay? So it's independent. Lots of such a situation. So so this is M is what we just determined. M is equal to sigma x squared and sigma xy, which is really same as expected value of x, y. This is e to the x squared. Okay. However, I'm writing the same thing with a different notation. Is equal to, don't confuse, I can rewrite this guy as e to the x minus mu x. Can I do that? Can I do that? 서로. Can I do that? I just wrote the same thing twice, but here the reasoning here is e to the x is equal to e to the y happen to be equal to 0, right? Otherwise it's going to divide like this. So y linear relationship is mx is equal to sigma xy. Oh, I'm sorry, I don't have to write this. This sigma x I can split into 2. This is y. I can write over divided by sigma y. Then if I do that, I have to write this guy right here. You see, I simply just put the dummy together. If I do that, then I can put out nice form x sigma y, and I can write as x sigma x. Can I do that? Say yes. Yes, so this is a nice final representation of correlated situation, correlated function. This is called sigma, the rho xy. What do you call the rho xy? Correlation coefficient, right? Or normalized covariance. Yeah. Normalized covariance or correlation coefficient. We'll use the name correlation coefficient. So this case over here is like this, x and y, right? And this is, in this expression, whether this is CG or CG is out here doesn't make any difference. If it's CG is way out here, the mean of x and mean of y are not 0, then you have to take into account the expression for this. For this, if mean is not equal to 0, then you have to take into account like this as a non-zero. Over here, assumption is this is 0. So unless this is not 0, then you have to express like that. Nothing to confuse it. And as you look at, then what happened for the regression line of x on y? What happened if this guy is y, if this guy is x? When I said have this, I think I made a mistake. I should draw the experimental point here. This is a y, and deviation is this guy, and this guy is my. I should write this. Then delta is equal to what? X minus my. Then if you do this, we develop all this for x and y, then using the same result from, this is what, don't make a connection, this is what we did. This is what we did. Then what you have to do, this is x. Change x to y. Change x to y. Change x to y. If you do that, then of course x to y. And if you do that, this guy will be x over sigma x is equal to this, whether flip or not, x and y, sigma yx is same as sigma xy, and this guy is like that, and this is like this, then this should be the result as a result of the analysis using that delta, minimize the delta, okay? So no differences at all, except the switching x and y. Then you got that, but for the other situation, you got this. Nothing to confuse. Don't confuse it. So usually this is the way we are always dealing. Set the x and y like that, okay? So this case is, oh, just a minute, yeah, this case is x and y is flipped. Now correlation, you can't neglect the correlation. When you plot the measurement point in the xy plane, then you can. So this is all done here, okay? It's all done. And final description using XY plot. So this is origin, not the CG, and this is X, this is Y, and mean value is not 0. It's not 0. Can you write that relations that we wrote? Yes. Y over sigma y is equal to sigma xy, sigma x, sigma y, x over sigma x. What's wrong in this equation? Anything wrong? This is not the CG. Mean value is still there. What's wrong in this expression? What's wrong in this expression? X has to be changed with y minus mu y, right? And this guy, sigma x square, has to be equal to not x, mu x square. Sigma y has to be e to the y minus mu y square, right? Yes. And what about sigma xy? Sigma xy, you have to add x minus mu x, y minus mu y. That has to be. And this is good for anything. When you move to the CG, then mu x, mu y is equal to 0. So this is pretty general expression. So it's right here, expanded. This is expanded, isn't it? No differences. So here is a mu y, and this case is, the vertical line is y, this is x, right? This case is vertical line is x, horizontal line is y. From this page, I want to do when I come back, because this bluntly saying that rho xy, the range of rho xy is -1 to 1. I want to really show you how you can say that. You can just say that, but we'll derive the expression for reasoning. But this equation set is what we have done. And this equation set, is nothing new. That's what we have done. But this is new. I'm going to show you how can I say correlation coefficient ranges between -1 to 1. Okay? And this expected value, the definition of this covariance is limit 1 over n. 1 over n is something like what? It's like a probability density function, remember. And this is, again, same as I is equal to 1 to all the way to n, which n goes to infinity, but in reality, n never goes to infinity. In our lifetime, always finite, we have to live. We know how to live with the finite, the value. Okay, I wish you have a good time next week. And after I come back, I don't want to give you, okay, 4-hour lecture. No, just a little bit at a time, 1 hour, 1 hour. But exam has to be 2 hours. So then 2 hours. Come back that day with a good light dinner, not heavy dinner, then you can think. Light dinner on April 4th, then have a 2 hour. I usually make, if it's a 2 hour exam, I make out the problem, comprehensive exam, then you can really do about hour. You don't need a 2 hour. If you have to spend the 2 hour, something not right. That's what I usually do. 1 hour sufficient. Usually 1.5 hours, not the 2 hours. Okay, I'll see you on 21st. Have a good next week.